Example 3, state the domain and range of each relation. So this is page 2 from chapter 1. The domain would be all the x values. And here I can plug in any number. This is linear, so any number would work. I'm going to just say it's all reals. That is the domain. Range. So domain I think of from left to right. How far left can I go? How far right? I can plug in anything. The range is also anything. I can get 0 for an output, a positive huge number, a negative huge number. I can get anything. So that would be A. B, the domain for this graph, I could plug in any numbers for x I want. That is all reals. But this time the range is not all reals. The highest output I get is 0. If not, they're lower than that. We would just say it's y is less than or equal to 0. And again, range are y values, so I'm going to write it like that. Example 4, state the domain and range of each relation. Well, the domain is the x values. It's just -2, 3, and 4. And the range are the y values. It's 0, 2, and 5. And then state whether the relation is a function. It is a function because for each x value, it's paired with exactly one y value. So this would be yes, it is a function. B, the domain would be -3, -2, and 0. Even though 0 occurs twice, I only have to list it once for the domain. And the range, the only y value that we get in each case, here we get -2, here we get 2. That's the range. This is not a function because 0 is paired with 2 different outputs. Definition of a function, for each input, it must be paired with exactly one output, and this is paired with 2 different outputs. Vertical line test is used to determine if the graph is a function. So I'm going to show you 2 cases, one that's going to be a function, one that's not. So the first one, if I drew a sideways parabola like this, this is not going to be a function, and it's not going to be a function, so I'm going to write no, but here's the reason why. Because if I drew a vertical line, it hits in more than one spot. So if you draw the vertical line and it hits the graph in more than one spot, then the graph is not a function. Next case is going to be a function because wherever I draw a vertical line in this graph, it only crosses once. So this would be no, this would be yes. Okay, example 5. Determine whether the graph represents a function. The graph here, I guess, is this shaded region here. And what's going to happen if I draw a vertical line, it hits the graph in more than one spot. If it was just the line, it would be yes. But if it's the region, it would be no. And my answer would be this graph, the shaded region, does not pass the vertical line test. I'll abbreviate that to VLT. B is a function because wherever I draw a vertical line, it hits the graph once. So this is yes, and the reason is the graph passes the vertical line test. Okay, function notation. Here's what this means. If I graphed y equals 2x minus 2, on my Inspire, if I try to type that in, which I have right here, there, if I go to graph, there's no y equals, it says f of x equals. So f of x is synonymous with y. That is function notation. If I graph 2x minus 2 here, that is the same as y equals 2x minus 2. So function notation means this. If a normal ordered pair is x comma y, in function notation, you can replace y with f of x. And usually as you'll see in the next example, when we're inputting values in a function, instead of writing them as y equals, we write them as f of x equals. So example 6, evaluate each function for the given value. This is f of x. It just says f of negative 1. So wherever you see an x, in goes negative 1. And you got to remember PEMDAS. So we first do parentheses. Negative 1 cubed is negative 1. We take the opposite of that, which is 1. And 1 minus 1 is 0. So we could say f of negative 1 equals 0. The next one, wherever you see an x, you plug in a 3. 3 squared is 9. 9 times 3 is 27. And the absolute value of 27 is 27. So these are the examples on page 2 from the chapter 1 notes.